Astronomers used Mirachs Ghost to learn more about formation of supermassive black holes. The source of fast radio bursts might have been found. Mini-neptunes aren't actually mini-neptunes? And also, there are water bears on the Sun? What? Let's find out. My name is Andrei, and this is Cosmos Elementary. The formation of supermassive black holes remains an unsolved mystery of modern astrophysics. This time, scientists decided to use ghosts. Well, a ghost. Mirachs Ghost, which is just an unofficial name of a galaxy NGC 404. It's a dwarf lenticular galaxy, and it got its name for being really close in the sky to the star called Mirach. Because of that bright star, sometimes it's hard to observe the faint galaxy. But what does it have to do with black holes? Astronomers have a pretty good idea how stellar black holes form when massive stars die. But supermassive black holes? Today we are aware of black holes tens of billions of solar masses. Black holes grow by consuming stars and interstellar material, but there are limits to that. Based on modern estimates, if the initial black hole seeds were regular stellar mass black holes, they simply didn't have enough time since the Big Bang to grow that massive. More than that, in the early universe during the first billion years we already observed quasars with billion solar masses black holes. The mass estimates are based on their luminosity. There are several hypotheses of what those black hole seeds were and how they formed. They could be remnants of first-generation stars or exotic quasi-stars, or the result of the direct collapse. And it's very important to know what was their initial mass. So scientists tried to constrain that with the help of Mirachs Ghost. It's one thing to estimate the mass of black holes in high redshift faraway galaxies, and it's a completely different story when the galaxy is relatively nearby and we can study the motions of stars and gas. According to the study published in the monthly notices of the Royal Astronomical Society, supermassive black holes in large galaxies aren't particularly good for that, because they've significantly grown since their formation. They consumed a lot of material, underwent mergers, and it's hard to say what the initial mass had been. But black holes in the centers of dwarf galaxies, which experienced fewer mergers, are probably way closer in mass to the initial seeds. So a better estimate of their current mass can help constrain the mass of seeds. NGC 404 is relatively close, only about 10 million light-years. These are images in visible and ultraviolet light. The mass of the central black hole can be estimated from motions of stars close to it. The new research used not only stellar kinematics but also ALMA data on motion of gas surrounding the black hole. Studying how the gas moves and accelerates closer to the black hole, watching how the black hole affects the gas gravitationally, one can estimate the mass. ALMA high-resolution observations of gas agree pretty well with stellar kinematics, and the mass of the black hole turned out to be about 500,000 solar masses. In this study, it's even called an intermediate mass black hole and not a supermassive one. That of course still doesn't answer the question of how those black holes formed, but at least now we know that the seeds could be less than 500,000 solar masses. Recently, European Space Agency released the first images of the Solar Orbiter mission. For instance, this animation. Wait, stop. Let's zoom in a bit. What is this? Don't tell this to the conspiracy theorists, because this thing was called a tardigrade on the Sun, but as a joke, of course. In these images, this thing looks a little like a water bear, but obviously it's not actually a giant mutant water bear on the surface of the Sun. According to the mission specialist, it's a camera sensor defect which will be accounted for in future observations. And now let's talk a little about exoplanets. Out of more 4,000 known exoplanets, only about 50 of them were directly imaged. The rest were discovered by indirect methods. But now we have some new directly imaged exoplanets. Recently, using the SPHERE instrument on the Very Large Telescope, astronomers took an image of a forming planet. Now, using the same equipment, they photographed 2 exoplanets, and that's the first ever image of 2 planets around the young Sun-like star. It's no secret that so few exoplanets were observed directly because it's just really difficult to do. They are way fainter than their host stars. Here it was possible because astronomers used coronagraph. It blocks the light of the star and allows to image planets, like in this famous example of the system HR 8799. Another factor is the age of the system. The star TYC 89987601 is about 300 light-years away. Suppose there were aliens there with the exact same telescope and they pointed it at the solar system. They would have a hard time trying to image the planets here. Because our system is old, over 4.5 billion years old, and our planets are way colder. The age of this system is estimated to be only 17 million years. Planets didn't have enough time to significantly cool down after formation, which means they are much brighter in the infrared and they are easier to detect. Both planets are gas giants. They are much farther from their star compared to Jupiter and Saturn. 160 and 320 astronomical units, and they are 14 and 6 times more massive than Jupiter, respectively. A system like this one is especially interesting because the star there is similar to the Sun. Alright, as we can see, it's not easy to study exoplanets. The spectrum of light that passes through the planet's atmospheres can tell us about their composition. The way the planet blocks the light of the star and the orbital period can tell us about planet's physical properties like mass, size, density, and so on. But still, there are a lot of uncertainties even in planets' classification. Based on what we know, there are some exoplanets unlike anything we see in our solar system. Hot Jupiters, gas giants with orbits very close to their stars. Super-Earths, probably rocky planets but much bigger than the Earth. And Mini-neptunes, less dense planets with masses closer to Neptune and probably hydrogen-helium atmospheres. And now, 2 studies question that. Computer models are very important tools for scientists. Models were used in the first study that was published in the astrophysical journal Letters. Authors claim that mini-neptunes could be an illusion. Well, not in the sense that they don't exist, but rather that the observed properties of large and not dense planets could have a different explanation. If a planet is close to its star, it's a subject of the intense irradiation. And some planets that are generally classified as mini-neptunes could actually be super-Earths, and not just any super-Earths, they could be ocean worlds. Intense radiation of a star can cause a strong greenhouse effect and create a hydrosphere in a state of a supercritical fluid. The state when the temperature and pressure reaches a critical point and distinct liquid and gas phases do not exist, and the substance has properties of both. In these conditions, the atmosphere can get inflated and there appears an illusion of a relatively large and not dense planet. That is supported by the second article in Astronomy and Astrophysics. According to scientists, something similar may happen in the famous TRAPPIST-1 system with the planets B, C, and D. Fast radio bursts. Since their discovery in 2007, their nature has remained a mystery. These are powerful and, as the name implies, fast bursts of radio waves. They last only for a few milliseconds. Today, tens of them are known, and most of them are single events, and only a couple of them are repeaters. Until recently, most of FRBs were extragalactic. Another interesting feature is that there is no emission beyond radio waves detected. Radio signals from space of an unknown origin. Of course, there were some speculations that those could be signals from alien civilizations, but there were also some more probable ideas. For instance, FRBs could be signals from neutron stars collisions, or bursts of magnetars, young neutron stars with extremely powerful magnetic fields. And now scientists have found a link between FRBs and magnetars. An international collaboration research was published in the astrophysical journal Letters. It's about a magnetar SGR 1935+2154. It is located in the Milky Way, some 30,000 light-years away from the Sun. In the end of April, the Integral Space Observatory detected a burst of hard X-rays. The burst alert system on Integral automatically alerted observatories worldwide about the discovery. Then Chime Observatory in Canada spotted the burst of radio waves in the direction of the event registered by Integral. Then it was independently confirmed by another instrument, STARE-2. Then astronomers managed to localize the burst and identify that the emission came from that magnetar. This is the first detection of radio emission similar to the fast radio bursts coming from a magnetar, so the study supports the idea that magnetars are the source of at least some of the FRBs. Links to all of the sources are down below in the description, and if you enjoyed the video, leave a like, comment and subscribe. Bye!